Hello everyone, welcome to this series of problem solving interview questions. My name is Ashish and today we'll be talking about a very interesting problem called the subset sum problem. Now this has been asked in various companies including Facebook and Amazon, and this is one of those problems which can be solved using various approaches starting from bit masking approach to backtracking, dynamic programming and memoization. Now I'll be starting off with a very naive backtracking approach today, and we'll try to see how we are converting our thought process into a recursive solution. Because it's better to start off with a foundation rather than directly jumping into optimized dynamic programming solution. And towards the end, we'll see if there are any overlappings and if there is a scope for improvisation. So yeah, let's get started. Now let's look at the given problem statement. The problem statement is, given an array of non-negative integers and a given sum, which is in this case is 12, we have to find if there exists a subset whose sum is equals to the given sum, and you have returned true or false. So in this case, if you see, the given sum is 12 and we have a subset which is 3, 2 and 7 whose sum is equals to 12. Again 3, 4, 5 is again 12, and so the answer would be true. Now what exactly are subsets? Let's take an example of an array 1, 2 and 3 and see how many subsets are there. So 1 is a subset, we have a 2, we can have 3, and these are all subsets. You can have 1 and 2, similarly 2, 3 and 1 and 3, 1, 2, 3, and we can have an empty subset as well. So total subsets we have here is equals to 8, or 8 equals, we can say 2 to the power 3, and 3 in this case is the length of the given array or the number of elements. So we can assume 2 to the power n is the total subsets we have. Okay, so since I mentioned the total subsets would be 2 to the power n, and in backtracking we have to generate all the possible subsets. That's what backtracking means. It's about taking all the possible combinations, whichever is possible. So when I start off with recursion, I always take care of one thing. Let's start off everything with a very small amount. So let's start off with an empty array. So in this case, let's say there is nothing in the array. So what all options do we have here? Well, no, only one option, that is to take nothing, right? So we have only one option in this case. Now let's take one element in an array, and an example, let's take 3. What all options do we have? How many subsets can be generated in here? So we have two options here. Either we can pick 3, which will be one subset, or we can exclude 3. We are picking 3 or excluding 3. In this case, there will be nothing. And if the given sum is equals 3, we have got our answer. If the given sum is 0, we have got our answer. Now, let's try to take 2 elements in an array and see what happens. So, take the first 2 elements, which is 3 and 2, and see what all we can do here. So the first element, what all option do we have here? Well, we can either take that element, which will be 3, or we can exclude that element, which will be empty. Now jump to the second element and see what we can do there. So at this step, we have again 2 options. We can either take the 2 or we can exclude the 2. So we take 2 along with 3 here. So it will be 3 and 2 in the subset, or if we exclude it, it will be the 3 alone. Similarly, when we have nothing, if we take the 2, in this case, we have 2, only 2. If we don't take it, we are still remain with empty subset. So we have these 4 subsets with us, and the sum is 0, here the sum is 2, sum is 3, and sum is 5. And if the given sum is equals 5, we have our answer, right? So one thing you can observe here is we have 2 options at every step, and what all we are doing here is we are incrementing from one index to another. We are jumping from one place to another in an array. So first thing is we are incrementing the index at any cost, right? Whether or not we are taking it or not. Second thing is having two choices, and we are figuring out all the combinations. Now when we are reaching at the end of an array, we are calculating if any of this sum match to the given sum. Now towards the end we are verifying it, right? We have to verify, and that's all we have to do. Now let's take these three things and try to write a code. Now, as I mentioned before, we have to convert our thought process into a working recursive solution. Now this we have is a thought process. We have to increment our index, we have two choices, and towards the end we need to verify, and this is the problem we are given. Now if we have these choices and we need to write a code, now let's start off with the first thing, that is writing a function. So let's say a function is, let's say its function name is subset sum. And what are parameters do we need? We need an array here. So we have array. We have the length of the array, say n, which in this case is 5. And the array is here. And we need an given sum, which is again sum, and this is 12 in our case. We need something called the index. So let's say index is mentioned as I. So index is the I. So that will be jumping from one element to another. We need to calculate the sum of all the subsets at every step, because we are generating all 2 to the power n solutions. So we need to track that sum somehow. So take the current sum. I'm writing it as cur sum, and this is, and yeah, that's all we need in our function. Now when we are writing a recursive function, we always need to take care of the exit condition. If we are not writing an exit condition, we are just ending up with an infinite function calls. So a base condition, and we'll come to that later. Now, so we have index incrementation and two choices. So these two choices at every step. So we are calling the same function again and again. That means we'll be calling this subset sum at every step with different elements, which will be the element at a new index. So let's say we are calling that function again, which is subset sum, or I'll just write it here, subset sum, and we're passing the elements, array, the length, the sum as it is. Now we're incrementing one element, one index. So the first index starts from 0. In this case the I starts from 0, so we have to increment. So I will be I++. Now as I mentioned, given an element, let's say the first element, which is 3 in this case, we have two choices, either to take that 3 or to exclude that 3. So let's take 3, I mean the first element. So we'll add that element into our current sum. Current sum initially is 0 because we don't have anything. So let's say current sum, and we're adding the first element here. So the first or the ith element. So in this case it will be array of I. So that takes off choice number 1, which is including the element. Now we have to exclude that element, but we have to keep the index incremented. So again it will be subset sum, the parameters are as it is. Now index will be incremented because it is not a choice. Now exclude that element means we are not taking or not adding it to our current sum. So it will be current sum itself, and that should be it. Now towards the end we have to verify. See, if we have to verify at the end, now it is not a proper way to write a code, but I'm just trying to map our thought process into writing a code, and you will see how we are building it up. So I think up to this is clear. Now let's take the third step, which is at the end verify. So we are incrementing the index from one element to second to third, and at the end we don't have anywhere to go. So that becomes our exit condition. So when the index I, which is this one, reaches towards the end, which is n-1, and n is 5 in this case, the length of the array, so n-1 is 4. So if our I, or the index, is greater than or equals n-1, that means we have reached the end. We don't need to process any further. We can just start our calculation. Now at this step we would have calculated our current sum with that particular subset. So if our current sum is equals to the given sum, because now let's say the given sum is 3 in this case, and we have one element. So towards the end we have found the 3 and we have added it to the current sum. So if that current sum is equals to the given sum, then we have found a solution and we can safely return true. If not, we can return false, else return false, and that should be it. Of course there are like some base conditions where we have to see if sum is 0 or not. If it is 0, it is always true, and things like that, but I'm not boring you with all these things. Now if you're returning true or false from the end and verify, and we're calling these two functions again and again because of these two choices, so we have to return this as a solution, and the return type will be boolean here. So just return this here. What do we return? We return the OR of it. Why OR of it? Because any one of them can return true, or any one of them can return false, or both of them can return true. So at this case, since we are verifying both the choices, we can take OR of it and we can return the final boolean solution, which will be the answer. So yeah, so that should be the whole code basically. So let's try to take a step ahead and see how these function calls are happening in recursion. So now taking the same thought process again, and we'll try to trace out all the solutions for the code which we have just written. Let's start from this array, and let's say we are tracking the current sum and the index, the current index, which is this one, which is index. Okay, so now let's start off with the first element, which is 3, or let's say we have we're just taking 3, and at 0th index we have only 3 for now because we have taken this element. Now if we take 2, because the function calls are happening in one direction, in the left direction, if you see, so 3 plus 2 becomes 5. So at index 1 we have sum of 5, current sum is 5. Again at 7 it will be 12 at index 2, which is 2. So now it is 16 at index 3, then plus 5, it is 21 at index 4. So now if you see, the given sum is 12, and at the end, which is 21 here, we haven't found a solution. That means in this graph we do not have a solution, and we take a step back, which is returning the false, as I mentioned in the last code given below. So it will return false from here. Once it returns false, it will call the element without taking the last one, which is the 5, because at index 3 it took the 5 and came up to 21. Now if it doesn't take a 5, which is the second condition, it will land with 16 at index 4 because it has excluded the last element. So now again the 16 is not equals 12, so it will return false again, and the same process will happen again and again, and 12 will be at 3. Now at 3 the sum is 12 because it has not taken 4. Now it will include 5, let's say, and 5 plus 12 will be 17 at index 4. Excluding will be 12 at index 4. Similarly, we can trace out the whole graph. Now, if you try to trace out everything, so at some point of time you will see, for example, at 7, at index 2, we have only 7, and if you take 4 and 5, we will land up to 16 and 4 at index 4. Similarly, we have found 16 at 4 at our previous solution, and for example 12 and 4 is an answer where we are finding our sum. We have found our sum 12 and 4 here as well. So we can see that there are a lot of overlappings, and this is just for the two elements which I have just traced out. If you trace the whole graph, which is the total of 2 to the power n subsets or n solutions, so you will see that there are like lot of calculations or computations which are happening again and again, and that's where we can improvise our solution by just storing. Maybe we can just compute it once and store it in a data structure, and we can use it later, and it will improve the efficiency. And exactly that approach is called as memoization. And this approach is a top-down approach, meaning we are coming from top and we're either choosing one or excluding one. This is a top-down approach. And the opposite of it, which is a part of it, you can say, is a bottom-up approach, where we will be building from small sum and a small integer and to a whole towards the end. And that solution is called as dynamic programming. So yeah, I think that helped in laying the foundation, and we saw how these things can be optimized, how we are having this all these overlappings and recomputation of things, and that will lead us to find a more optimized solution, which is the memoization and dynamic programming. So in the next video, I'll be discussing about memoization, and we'll see how this problem can be, how this exact code can be converted into memoization with pretty ease. I think that should be it for now. Stay tuned to this and do subscribe to my channel.